Hello and welcome to the lecture Few Short Learning. In this lecture, we are first to understand what is the problems of zero short learning. Namely, we discuss Hubness problem, domain shift problem, bias problem, cross-domain knowledge transfer problem, etc. And then we discuss some application of few short learning. Then we introduce the few short learning. We start with definition. Then what do we mean by support set and query set. Then I try to understand what is meta learning and how we can understand what we mean by learn to learn. So, as we have discussed the zero short learning in the last lecture, we find that there is some problems in conventional zero short settings. First is the Hubness problem. Now, first we read out the things and then try to understand what is the problem. Okay, so in high dimensional space, some points, they call it hubs, we'll see later how it has been defined, tend to appear as the nearest neighbors of many other points, even if they are not truly similar. Let we understand, we take an example, try to understand. These points dominate nearest neighbor searches, and other points called anti-hubs rarely appears as neighbors. So ultimately what we have to understand in the zero shot learning, what we are doing, we are basically doing at the testing time, from the testing sample, we map to the semantic space, and there is some class embeddings are there of this particular, and we find which is the, it is in general, or it is our observation that what we are predicting in space, in class or semantic space, and what is the class embeddings, it will be nearby, and that's why we use this kind of nearest neighbor search. Now, generally what happened in zero shot learning, that we map the visual features image to semantic space, attribute matrix, then classify unseen classes using the nearest neighbors. Is that what we have just said? Now the problems happens, some class prototypes or embeddings become hubs. So hubs means where the some space or some clustering kind of thing, where the probability of unseen classes will be high. So many test samples get incorrectly mapped to these hubs. This leads to the biased prediction and poor generalization, and as a result certain classes are over predicted and while others are almost never predicted. So we have to try to understand this. Okay, so first we try to understand this. Now here this is the similar kind of, now this clustering is called hub. Okay, now this, why this is called hub, you can see here, you can that these are the different kind of image embeddings to this mapping, the class embeddings here. And now even if these are the actual things, this has been misclassified within the hubs. So now this is the basic understanding of Hubness problem, that given such a hub, that there is some sort of tendency that at the testing time, when we are mapping from feature space to semantic space, then and we use the nearest neighbor, it maps to the some points within the hub, not actual classes, and that creates the Hubness problem. Now imagine a semantic space where one class embedding sits near the center. Many projected image feature cluster around it due to the noise or projection bias. That class becomes a hub, even if it's not the correct level. So cause of hubness in data set, high dimensional embedding. So what vectors, attribute vectors, and domain shift, that unseen classes is not that. There is some projection bias, mapping from visual to semantic spaces in part, and the distance of concentration. The distance between the points becomes similar. So these are the general. So what we understand here, that this becomes hubs, and there is a tendency of the nearest neighbor search that you put the unseen classes within the hubs. But in actual, these are the distant class, and that is called the hubs or hubness problem. The next thing is domain shift problem. A domain shift or distributional shift is a change in the data distribution between an algorithm's training dataset and the dataset it encounters when deployed. Now here you just see. Now let try to understand, or let there is a situation that this bag images is color images and your model is trained by these color images. Now when testing, these are the grayscale images been given. So it's a, in general these images in a different domain. So two domains are different. If this kind of domain difference are there, then this domain shift problem happen. Since distribution of the training and testing data is different, because the color image is a grayscale image. Model performance for testing is generally lesser than training, and this is called the domain shift problem. This phenomena is more severe in ZSL, zero-shot learning, since the seen unseen classes are disjoint. So this example for domain shift, the bags with domain 1 do not have any background, while those from the domain 2 have some complex background. This is another thing. That this has a background, this is not a background. The classifier trained on one domain will suffer from the performance degradation when it tested on the other domain. So first is it is a color image, it is a grayscale image. Then there is no background here, but it's a background here. So this is called the domain shift. And this is severe dataset because seen unseen class are disjoint. Next is the bias problem. While ZSL training, the image and level access is limited to seen classes only. So model becomes biased towards the predicting seen classes as correct classes more frequently at the testing time. This is because of the generalized ZSL. If there is a both training samples and testing sample and in the test set, then this biasness problem is model is biased towards the training sample or seen samples. The bias problem hurts more in the case of generalized ZSL. Test set has images both from seen and unseen classes. So a biased model generally categorizes unseen class example as a seen class example. So result is accuracy dips drastically. So this is the bias problem that we have to understand is very easy to. This is a very common problem. Since our model is trained on the seen class, if our testing set contains both seen and unseen class, definitely there is a biasness to the seen class rather than the unseen class, and this is the biasness. Next thing is the cross-domain knowledge transfer problem. Now, prediction power of a ZSL model will depend upon the ability it gain to bridge gap between seen and unseen classes. This gap is bridged by a semantic space that we understand. That is the basic idea of ZSL. So the knowledge transfer from visual to semantic domain and vice versa is crucial. Now both of these domains are very different in nature. One very high dimensional, another very low dimensional. This feature space is very high dimensional, while the semantic space is low dimensional. This mapping should have enough discriminative power. For example, during testing, models should understand the beard-like properties along with the attribute white. Otherwise, may label it as a grizzly bear. So that is very important. So cross-domain knowledge transfer is very important, and mostly because the image feature is very high dimensional, while the semantic feature is relatively low. Okay. Now we quickly look what is the application of zero-shot learning. In case of image classification, we have seen there is some rare species. It means the labeled example is very much unavailable, where this zero-shot learning may be used. Or medical diagnosis, some rare diseases, where the pathological reports in any modalities. Maybe X-ray, maybe MRI, CT is not available. Some NLP is a new concept. There is a very kind of novel concept. So there is no very, you can say, examples are available that and recommended system. So these are the basic application and many more others can apply it. Now we are going to discuss another very important topic, that is few short learning. This time we go a bit superficially and due to the time constraint. Now what do you mean by few short learning? That given this, and can we say that this particular image is armadillo or pangolin? Now the question is that just if these two sets, there is some data set is given and there is a single image. Now by inspecting the similarity, we can say this is pangolin. Okay, so this thing we understand, and we will see later this is the backbone of this few short learning. Now what we mean by few short learning? Number of labeled images is too few to train a deep classifier. If this is the situation, we generally use the few short learning. So few short learning is a technique where a model learns to recognize new classes using only a small number of labeled examples, typically 1 to 10 per class. So that we have to understand. We have a very few training samples or labeled samples at the training time. Definitely, if we have to use that conventional supervised paradigm, then definitely there will be a chance of overfitting, and generally model is not learn anything. It's so little or so small data set. So what is the counterexample? Now this is the training set, you can see. So there is a one of dog, elephant, tiger, macaw, car, and so on. Okay. Now here in few short learning, one very interesting terminology is called meta learning. And one part of, or one, you can say, instance kind of learn is learn to learn. So how do we learn? Can we learn? How we learn something? So this is that. Now given this data set, it is a big data set. So we can do this, the supervised learning. Now that the goal is not to train the model conventional supervised learning. So this is given this data set. So what is our goal here for this learn to learn? That is, let the model recognize the images and the training set and then generalize to the rest test set. This is the basic objective of conventional supervised learning, but at this moment it is not our goal. So what we want to, in few short paradigm or few short learning, that is learn to learn, is trained on difference and similarities between object and classes. Now given this data set, we try to find, we are not find, oh look, this is a husky, this is elephant. What is done in unsupervised learning? Here what we are doing, we are trying to find out what is the difference between husky and elephant. What is the difference between elephant and tiger? What is the difference between elephant and macaw? What is the difference between husky and macaw? And so on. So difference and similarity between interclass or interobject in a data set. Okay. Now, if the question comes, given two images, are they same kind of objects? If we learn in this learn to learn fashion, then our model trained like in this way, that can easily say yes, these two are same images. So we can say, since model is trained on similarity and difference, it can answer it correctly, although it's never see the squirrel in the training set. You could see that there is a squirrel is not training set, but it is learned that two given two images, that what is the similar image or different image. By virtue of this learning, it can say, okay, this is a similar image, both images same kind. Same thing if it is given these two data, you will say no, it's not same, not a same image, it's a different image. So the model can answer the two objects are different, but both the things they never see. The bulldog sees, or this pangolin is never seen. So model knows that image of two objects are very different, but both the classes are not in the training set. So model never see. Even if the model never see the image in the training set, they can at least say these two are not same image. Okay, that is the basic essence of learn to learn. Now come to the few shot learning. This is a query image. Now if this is Ming, then what is this image? Our trained model based on the difference and similarity cannot say, because never come across this image before. It is not within the training set. Model can't answer this question, it never see this. Now if with this we give another set of images, let me say the support set, and now ask what is this image. Now you can see this image is very close to this order. So by virtue of just that this is similar and these are all these pairs are different, it can say model can answer this order, because it finds maximum match between the query image and the image order in the support set, even if it don't come across at the time. With the help of this support set, you can do this. Okay. So what is support set? A set, a very few level data example, but exactly in our case for each of these classes, few sets. Support set is small. It is not possible to train a deep model using support set. Definitely, it's not required. Also, we are trained is our model is trained on a big data set and based on the difference and set. Now it only provides additional information at test time, and query image the image to classify the test time. With this setting, we can very easily do this. So the deep model is trained using a big training data set that we have. Rather than training a model to recognize a specific object such as dog, cat in the training set, the model is trained to know the similarity and difference between objects, not in the conventional supervised way. Now this model is trained to know the similarity and difference between objects. The trained model now can identify the query image is present in the support set or not by seeing the similarity between them. And query image is the image given. Now this is the basic essence of the fusion. Now here you can say the same question. That's why this is the support set, this is the query image. This come to the very first slide, yet it can say that yes, it is pangolin, because just a similarity. So few shot learning is a kind of meta learning. Learning is learn to learn, is answered by comparing. So this is the basic idea. Now here we can say the same thing. Supervised learning, this is the test sample, because if it is given, it is in by virtue of this Husky, you can say test samples are from the known classes, so it can say that it is Husky. But in few shot learning, this rabbit is not in this class. Query sample are never seen before. Query samples are from unknown classes. So by virtue of the supervised learning, it cannot say. But if there is some support set is there and there is a rabbit class, but you know that the difference and similarity by virtue of this big model Now model can answer, okay, this is rabbit because based on this rabbit, this support set we understand. These two are very close and very similar, so it's a rabbit. That is the basic idea of the fusion learning. So there is some nomenclature, the k-way n-short support set. K-way means the support set has k number of classes, 2, 3, 4, 5, 6. So this is 6 way. And n-short, for each class, how many number of samples? In this example, only one sample. So this is a 6-way one-shot support set. And like normally, in general, we say k-way n-short support set. And this prediction accuracy, you can say, if the number of ways, you can say, number of classes is high, definitely it is very constant accuracy is coming to decrease, is decreasing with increasing of number of classes. Or number of sorts, definitely the accuracy is increasing with increasing of number of example per class. So in summary, what we have understood that in this particular lecture, the challenges of zero-shot learning, the Hubness problem, domain shift problem, bias problem, and cross-domain knowledge transfer. And then we discuss some application of ZSL. Then we briefly introduce that few-shot learning, just define it, what we know, what is support set and query set, and what is the meta learning and learn to learn. This next lecture will start multimodal deep learning. Thank you very much.